Hello everyone and welcome to another video. Today I'd like to continue our discussion regarding how to keep track of the attitude of an object in space using Euler angles. If you recall, we started this discussion by first defining the Euler angles and the Euler rotation sequence. We then looked at applying the Euler kinematical equations and Poisson's kinematical equations to develop an algorithm that consumes rate gyro information and converts them to Euler angles. If you haven't seen these two videos first, please make sure you watch them now because we're going to build off a lot of the concepts we developed in these videos. Links to those are in the description below or by clicking in the card up in the upper right of your screen. Now, we saw that while the Euler kinematical equations and Poisson's kinematical equations techniques were effective, they had some potential singularities that might cause some issues at certain orientations. Well, as they say, there's more than one way to bake a quesadilla, so today we're going to look at a third technique that hopefully addresses these shortcomings. So, if that sounds like more fun than a room full of puppies, why don't we jump over to the whiteboard and get started. Alright, so the mechanism that we're going to use to address these shortcomings are known as quaternions. Okay, so the idea with a quaternion is that instead of using three Euler angles to represent the relative attitude of two frames, we can use this concept of a quaternion to try to represent that same relative angular position. So the idea with the quaternion, a quaternion here, it's a 4x1 or a 4-element object here. So let's denote this as Q. You'll see in a lot of lectures, a quaternion is denoted as Q. So it's a 4-element object here where there's a scalar part usually in the first entry and then a vector part in the next three entries. So you could think about this as, let's call it maybe a Q scalar and then like a QX, a QY, and a QZ. Or, you know, again, if you want to just think about this as four numbers, how about just a Q1, Q2, Q3, and a Q4. Okay, so again, in this formulation, S here is the scalar part of the quaternion. And then V here is a 3x1 or 3-element vector part of the quaternion. So again, you can either think of it as a 4x1 or a 1x4. Some programming languages like MATLAB like to put this in a row. I like to think of them as a column. It really doesn't matter as long as we just think of them as a 4x1 or a 4-element object. Now, the idea is, what do we want to put in here? What is this scalar part and what is this vector part? Well, the idea with a quaternion is it's sort of, in order to use it to represent a rotation, it's based on Euler's rotation theorem, which states that, right, the relative orientation of two frames can be described by only one rotation about a single axis, right? In fact, we talked about this example exactly when we were discussing the Euler angles. And in fact, this is so important that I think we better flash up the animation here, and then this will hopefully jog your memory what we were talking about. Remember, we said that if I'm trying to rotate from a northeast down to a body frame of a vehicle, I can use three Euler angles to do these three subsequent intermediate rotations, or I rotate about a single axis, which we were kind of drawing in this animation with that magenta line. Again, I've got a link to that video, and in fact, to that exact timestamp of where we were talking about how to get this single unique axis of rotation. Here, I'll put that link in the description again with the timestamp. So the idea is, instead of rotating about three of those subsequent axes, can we just embed that information about that single axis, right, that dark magenta line, as well as how far do we rotate about that unique axis, right? We'll call that rotation angle or that translational angle maybe theta. So the idea is, can I put that information about the axes and the rotation into these four elements of the quaternion? So in our situation, what we want to use the quaternion for is, again, embedding that type of information. So what we're going to use is, again, we got a Q scalar, and then we've got the QX, a QY, and a QZ, right? Three elements. The first scalar part, what we're going to do is we are going to use that angle theta here. So maybe let's first define theta here. So where theta is it's the rotation. Some people don't like to call this like the rotation angle. Maybe they call it the transformation, just to denote its difference from like a rotation about a single axis. This is a rotation about this unique axis that we're talking about. So theta is this rotation or transformation angle. Okay, so to embed that, we're going to put this in the first element of the quaternion. However, we're not going to take the angle itself. We're going to divide it by 2 and take the cosine of it. Okay, so this has the angle information embedded in the first slot, right? The next thing we have to do is we have to embed that, that axis of rotation, right? The magenta line that we were talking about. So let's call that thing E, how about? So this is our normalized axis of rotation. Okay, so again, it's a unit vector. You should make it a unit vector. If it's not, make E a unit vector here. And it's a 3×1 vector. Right? Okay? So again, we could stick that now here in this 3×1. I could just put E here, right? And that fills up this 3×1. But again, we're not going to just use and directly put in E. We're going to multiply this by sine of theta over 2. Right? So here you've got the vector part multiplied by just this scaling scalar. But long story short, I think everyone can see now how this 4×1 element, these 4 numbers, this embeds basically the same information, and actually more, but embeds info about an arbitrary rotation. Right? You can see the axis of rotation here, and then you can see how far do you rotate about that axis through theta. Okay? So maybe before we leave this, we should make a couple of notes. This definition may change depending on different programming languages. Some programming languages, when you're dealing with the quaternions, they might use a different way of embedding the rotation angle and a different way of embedding the axis of rotation. But we're using this notation because this is consistent with MATLAB's aerospace toolbox. So there's a lot of functionality in this MATLAB aerospace toolbox that's going to allow quaternion manipulations. And when you see a quaternion in MATLAB, this is basically what they're doing here. So you can use that once you see a quaternion in MATLAB. You can try to extract the rotation angle as well as the axes of rotation if you like. The other thing that maybe we should note here is, unfortunately, we've run into a little bit of a naming collision here. So for this discussion, this lecture, and as well as kind of whenever we're talking about quaternions, we're going to use Q to denote the quaternion, right? It is not the pitch rate. Right? Remember earlier in our previous lectures we had P, Q, and R, which were the roll, pitch, and yaw rate respectively. Well, you see there's a slight problem with Q and Q. So tell you what, let's use this. Let's agree that Q stands for quaternion. Furthermore, you may notice that theta earlier, right? Right now we're using theta as this thing. It's the total transformational rotational angle. So it's how far do you rotate about this axis E? So that is the transformational, I guess, angle, or the rotational angle. Again, this is sort of one reason why I think some people call it the transformation or the transformational angle. It's about E. It's not about one of the primary axes X, Y, Z. I think that's what we're trying to denote here. So theta, this is a transformational angle, right? And this is not the pitch Euler angle. Right? Earlier we said that all the Euler angles we were capturing in capital Phi, which was phi, theta, psi, for roll, pitch, yaw angles. Well, we're not when I say theta in this lecture, let's not. I'm not talking about pitch angle. I'm talking about the transformational angle rotating about E. Right? Okay. So. Okay, we've got the definition of the Euler angle, or sorry, excuse me, of the quaternion, and and we hope we understand kind of the physical intuition about what these are. I think what would be actually useful is let's go over an example of this now. So give me a second to pause the camera, erase the board, and we'll hit an example. All right, so the example I want to look at is actually the exact same rotation that we looked at in our previous lecture when we were discussing the Euler angles and the Euler rotation sequence. Namely, we had a yaw rate of 70 degrees, a yaw angle of 70 degrees, a pitch angle of 130 degrees, and a bank angle of 25 degrees. And if you remember what we did in the previous discussion was we basically turned this into an entire DCM, right? We turned this into a single direction cosine matrix, which which took us from the northeast down frame to the body frame, right? And this was a function of phi, theta, psi, right? This was kind of an ugly 3x3 matrix, but what we did next, right, was we looked at the eigenvalues and the eigenvectors, right? And what we did is we found the eigenvector associated with the unity eigenvalue, and that basically gave us the unique axis of rotation that we could have applied instead of applying 3 subsequent rotations, right? So this basically gets us our axis of rotation. Let's call that n for now, okay? So maybe what we should do is, to refresh your memory on this process here, let's pause, let's go over to MATLAB, and let's walk through till we get to this step, right? And once we have the axes of rotation, if you also remember, what we then did is we started to blindly just sort of guess and check, start rotating through about this axis through various angles mu. This was our left-handed Rodrigues rotation angle. I'm spelling rotation angle. Right, we just started making left-handed rotation through angles about these axes until we got the northeast down frame to line up with the body, or with the body frame that we expected from the Euler sequence again. So I want to go through this. Let's do this in MATLAB. Let's get to this point, and then you know what we can start doing is we can start then trying to see if we can embed this entire workflow, right, of using the Euler angles and all of this stuff. Can we find out what is the equivalent quaternion that would represent all of this equivalent stuff? Okay. So tell you what, let's pause, go to MATLAB, and get to this point.
All right, so this is virtually the same script that we went over in our Euler angle lecture. So as you can see, we're just going to define our Euler angles. We will then go ahead and compute the total direction cosine matrix to rotate from the northeast down to the body frame here. And then what we're going to do is we're going to get the eigenvalues and the eigenvectors. Just to refresh your memory what we did here. And we were looking for the eigenvector that was associated with the eigenvalue of unity, right? We said we showed that is basically the axis of rotation of what this rotation matrix is going to do. So we saw that was the last eigenvalue, so in the 3rd position. So we pulled that off and use that eigenvector as the axis of rotation for our Rodrigues application, right? So that's what we did in this for loop that I think we showed earlier. Is I'm basically just drawing the picture every once in a while after we rotate through, and I think, let me scroll back up a little bit. Yeah, you see right here, I guessed and checked at this number. I kept increasing and decreasing this angle of 233.5 degrees until it looked about right. So just to make sure that we're all on the same page, let's rerun this guy. I'll put a pause, a breakpoint right there. I'll dock the animation, and we'll give this thing a little bit more room just so that we can see that we're all on the same page. Okay, so I'll let this guy run. And again, we saw that what was going on here is we were rotating the northeast down frame, which was the red frame, about the magenta axis, and we were going to see if we could get it to the body frame, which was this blue frame here. And you can see as we increase this left-handed rotation, keep in mind, mu is a left-handed rotation about the axis that's drawn here in magenta, right? And we see that eventually we get it to line pretty darn close up. Okay, so this is a pretty good well, I don't want to call it approximation. It is what it is. But what I wanted to do here in MATLAB was make sure that we were able to get, let's go ahead and, oops, sorry, let me put the, the CLC over here. We want to see what is the axis of rotation n. So here, this is that axis of rotation, which was that magenta line, okay? So armed with this information, we have enough now to compute a quaternion. I guess we have to combine that with the angle that we rotated through, right? So we rotated through 233.5 in a left-handed fashion. So what we want to do is to see, can we embed the information of this 233.5 degree left-handed rotation about this axis as a quaternion? So let's jump back over to the board.
All right, so we saw that we ended up with the axis of rotation, right? We said that was, what was this, minus 0.48, 0.87, and 0.09. Okay, so here was our axis of rotation. And then what we also said is we saw that just by kind of blindly guess and checking, we had a mu of about 233.5 degrees, right? So we saw that by rotating about this axis through an angle left-handed, I'll write that LHR for left-handed rotation, about through this angle, we approximately got an equivalent scheme of these three rotations, right? We were able to rotate the northeast down to approximately this body frame. I'm going to keep saying approximately because, as you can see right here, this was a guess, right? This was best guess of how much we had to rotate about this axis to get those two frames to align. Nevertheless, with this, we have enough information that we can compute a quaternion that represents this rotation through this angle about this axis, right? So in order to do this, we want to go ahead and compute Q, our equivalent quaternion, which represents this. Maybe we should have kind of like a two-way arrow, kind of saying that it's representative, right? Okay, so the first thing we should probably do is let's get rid of this left-handed rotation, change that to a right-handed rotation, right? So let's say theta is just going to be minus mu. Okay, so that converts from the left-handed to a right-handed rotation, so theta is a right-handed rotation. Furthermore, I kind of want this number to be positive just for convention, so you know what, I can add 2 pi, right? Just adding multiples of 2 pi doesn't really change the angle, okay? So if you do this, numerically, I think this comes out to be, I don't know, about, well, it actually comes out to be exactly 126.5 degrees, and again, but I'll store this in radians, okay? Okay, great, that is theta. Next, what we need to do is we need to calculate the normalized axes of rotation, okay? So I have the axis of rotation, n, but we got to make sure that this thing is normal. So let's go divide by the norm. And surprise, you know, actually MATLAB already kicks that out in a normalized fashion. So this does just stay kind of 0.48, 0.87, and 0.09, okay? Okay, so at this point with theta and e, we basically have enough to go ahead and calculate our quaternion, okay? So the first thing we should probably do is let's go ahead and get the scalar component of the quaternion, that was s, and we said the scalar component of the quaternion was the translation of the rotation angle, right? 126.5 times pi over 180, right? But we're going to divide that thing by 2 and then take the cosine of that. Okay, so here's the scalar component. This comes out to, I don't know, 0.45, something like that. Okay, and then the vector component of the quaternion, v, right? We said that, okay, the way you get that was, let me just make sure I got the notes right. Okay, yep, this was e, which was this guy. Here's e. Right? Then you take the axes of rotation, negative 0.48, 0.87, 0.09, okay? But then we're going to scale it and multiply it by sine of the angle here, right? So 126.5 times pi over 180 divided by 2, right? Okay, so if you do that, you come out with a number, and crud, I ran out of room. Tell you what, let's go ahead and write it up here. So Q, at the end of the day, what we end up with, computed during this fashion, is our 4-element number, which is, okay, the scalar part is 0.45, and then if you were to multiply all this stuff out, you'd end up with minus 0.4327. Oh, sorry, I'm using more sig figs than I did earlier. Let's just leave it like this. This is close enough. 2 sig figs illustrates the rough idea. 0.77, I actually get 0.78 here, and finally 0.07. Actually, this is closer to 0.08 for sig figs. Okay, so that's what we get. So this quaternion here is approximately, well, actually, tell you what, let's say this. Let's see. This quaternion exactly represents this rotation, right? Now, this rotation is approximately this. So we should maybe be a little bit careful. Let's make all these connections. This is approximate, right? And the reason I say it's approximate is because we got the axis of rotation right, but we kind of guesstimated at how far we needed to rotate through the axes to make this rotation sequence equivalent to this rotation sequence. So these are a kind of half and half. This rotation is exactly represented by this quaternion. Of course, I dropped a whole bunch of sig figs, so again, maybe it's a bit of an approximation, but long story short, I hope we see how these are connected at this point. We're going to go through later, so keep this in mind. We will go through later exactly how to compute what should this number have been, like how far do we need to rotate about this axis to get exactly this same Euler angle representation, okay? But long story short, I think we've got a good framework now of what the quaternions are, what what elements or what goes in each element, let's take a moment to pause the camera, erase the board, and I want to talk about some mathematical operations on quaternions. All right, so let's take a moment to talk a little bit about some quaternion mathematics. So in other words, I want to do a couple of operations on these quaternions. Maybe the easiest thing to start with is let's talk about taking a norm of a quaternion. And as you can probably expect, we said that a quaternion is kind of just a 4-element vector. So its norm, you can either 1 bracket or a 2 bracket, however you want to think about it. Maybe let's just draw it with 1. Basically, this is the norm of a quaternion, and it's pretty much your standard definition of what you would expect from a vector. It's just square root of sum of the squares, right? So I have qs squared plus qx squared plus qy squared plus qz squared. So it's pretty much your standard vector 2 norm, okay? Again, you can use this norm to normalize a quaternion. So a normalized quaternion, right, is basically you take the quaternion divided by its own norm, and this gives you like a q unit vector if you want to think about it, or a normalized q. Okay, so that's pretty easy. Okay, how about another operation? How about a conjugate? Okay, so a conjugate operation on a quaternion, let's denote that as q star. Okay, it's basically you keep the scalar part the same, and all you do is negate the vector part. So qx, qy, negative qz. Okay, so that's how you would go ahead and do a conjugate of a quaternion. How about the inverse operation? Okay, and this is not necessarily a matrix inverse as you would probably expect, but we can denote this here as q to the negative 1. So this object, which we're calling the inverse of a quaternion, all you do here is you basically take the conjugate of the quaternion, a la here, and then we divide by its norm, a la over there. Okay, so that's what this object is. And again, we can think about this later on down the road, but this is not a matrix inverse in that sense, right? The quaternion is a vector, so this is some other entity. Okay, how about multiplication? Okay, so multiplication, if you've got 2 quaternions, let's say q1, which looks like a s1 and a v1, and you've got q2, which looks like an S2 and a V2, right? You can define the multiplication or the product of these things. Let's say Q is Q1. Maybe you might see this denoted something like this for the product operation or a multiplication operation. So this is defined as basically you get a new 4x1. Okay, the scalar part of this is just going to be S1 times S2 minus the inner product of V1 and V2. Okay, so this is a scalar portion. Maybe we'll draw this line here. And then the vector portion of the resulting quaternion, it's going to be scalar portion 1 times vector portion of 2 plus the scalar portion of 2 times the vector portion of 1 plus the vector portion of 1 crossed with the vector portion of 2. Okay, so I don't think it's worth it to really go through any examples. I think all of these are pretty self-explanatory formulas and definitions of how to compute these different things. But if you ever needed to take the norm of a quaternion or multiply 2 quaternions together, you can do this. So the thing that's more interesting, though, is how do we use quaternions now to represent attitude, and how do we go between things like direction cosine matrices and quaternions and Euler angles and quaternions and vice versa. So let's pause the camera, erase the board, and jump into that next. Okay, so this is where it starts to get interesting. What can we do to use quaternions to represent attitude? So let's talk about attitude representation with quaternions. Okay, so for this discussion, let's go ahead and consider a direction cosine matrix or a DCM of how about something that rotates from the northeast down to the body frame, as we've discussed in the past. And let's call this, it's again, as you know, it's a 3x3 matrix. So let's just call these entries C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay, so we're going to be using this as we formulate the rest of our equations and discussions. A quick side note, you have to be a little careful of what references you're looking at. Some other references, maybe let's write this down. So other sources may formulate based on C from the body to the northeast down. So the transpose of this. So again, this is almost like a matter of perspective. You got to be a little bit careful of which one are you talking about. So I'm going to be using this notation because this is kind of how we've developed all of our expressions. So I'm going to assume that the direction cosine matrix that we're talking about is going from the northeast down to the body frame, okay? So that's when I say C11, C12, all these entries, I'm talking about this matrix. If you're reading some other source, I mean, I'll leave a link to one of the sources that I used to develop these notes in the description below, but that source uses the exact, not the exact opposite, but you know, the opposite notation here, right? So you got to be a little bit careful, okay? So with that being said, let's talk about really the game plan. Maybe we can do this down here. We'll just draw like a high level overview, right, of what we're trying to do. Is I think we were all comfortable talking about Euler angles, DCMs, etc., right? Basically, Euler angles phi, theta, and psi, right? Now, what we're interested in is, can we represent all of this same information, right, with quaternions? Okay, so what I want to talk about now is, what is this mapping? How do I go from a DCM to a quaternion or vice versa? Or how do I go from Euler angles to a quaternion and vice versa, right? Because like we said, quaternions are hopefully representing this same sort of information, but in a more robust fashion, right? So there's got to be a mapping between the two, okay? So that's what I want to get into right now. So let's talk about the first one. How about if you want to go from a DCM to a quaternion? Okay, so this is actually an interesting one, and it's sort of a multi-step process. So maybe let's write that down. So this is a multi-step process. So again, the idea here is I want some kind of way, mapping, algorithm, however you want to think about it, where what gets passed in here is a DCM. In other words, that thing, C, V with respect to B. So the DCM to go from the northeast down to the body frame, you throw this in. You throw in a 3x3 matrix, and what comes out the other end is a quaternion, right? Q, which represents that same thing. So I want this function here, which basically goes, you know, it takes a DCM, turns it to a quaternion. Something like that, DCM to quat, right? Okay, so it's a multi-step process. So the first thing we're going to do, maybe let's call this thing step 1, okay, is we are going to calculate this weird quantity. So calculate this quantity. I'm going to call it Q tilde. It's not really a quaternion yet, okay? So this Q tilde is a 4x1 element. Let's call it QS tilde, QX tilde, QY tilde, QZ tilde, okay? And what this guy is, it's a 4x1. This first element is square root of 1/4, excuse me, 1/4 of 1 plus C11 plus C22 plus C33. So basically, the 1 plus the trace of the DCM is this first term. The second term is square root of 1/4 1 plus C11 minus C22 minus C33. Okay, the third element is square root of 1/4. I think you're seeing a pattern here, right? 1 minus C11 plus C22 minus C33. Okay, and the fourth element is square root of 1/4 times the quantity 1 minus C11 minus C22 plus C33. Okay. So you calculate this weird 4x1 matrix, which looks similar to a quaternion, but it's not, okay? Oopsies. Okay, so the next thing then we're going to do, step 2, is you're going to find, find the max entry in Q tilde, okay? So literally, you're going to find, I'm going to call this thing, how about Q tilde max? And all this is going to do is you're going to look for the maximum value of all of these. So you're going to look, you know, which one, QS, QX tilde, QY tilde, QZ tilde, which one of those is the largest, okay? So once you find that, what we're going to do here in step 3 is we are going to calculate the quaternion Q using the following table. Okay, so the following table here is what you're going to do here is this is going to be a 4x1. Tell you what, let me erase this. I think we all hopefully have this in our notes at this point. Maybe I'll just erase the first entry. Now let's get rid of the whole thing to be consistent. Okay, okay. So let's build ourselves a table. So what's the easiest way to do this here? Okay, 1, 2, 3, 4. Okay, there we go. Okay, and then 2, 3, 4. Yep, good. Okay. Okay, so down here you're going to look up what is the max value. Okay, so if QS tilde equals Q max, right? If this was the largest value, then what you're going to use for the QS, QX, and QY and QZ are as follows here. So for QS, you're just going to use QS tilde. Okay, and then for this element, you're going to use C23 minus C32 all over 4 times QS tilde. Okay, and then this element, it's going to be C31 minus C13 all over 4 QS tilde. And then this last element is going to be C12 minus C21 all over 4 times QS tilde. Okay, so again, this is what happens if QS was the max. If that's what you found in step 2, that this was the largest element of all 4 of those elements, you would then go ahead and compute the quaternion using these entries for QS, QX, QY, QZ, right? Okay, let's just keep going. So the next one is, what if QX tilde was equal to Q max tilde? Right? So now we're in the cases, this was the biggest one. Okay, the way you're going to recompute all of these elements of the resulting matrix or the resulting quaternion here is C23 minus C32 all over 4 QX tilde. And then this is going to be QX tilde. And this is C12 minus C21 all over 4 QX tilde. And then, oh, sorry, did I look at C12, C21, C31 minus C13 all over 4 QX tilde. Okay, great. And I think you see the pattern at this point, right? So I'll quickly fill in these last entries here, and maybe I'll just continue letting the camera roll and dictate in case it's hard to read these elements or if my handwriting is not terribly legible. Okay, so this element right here, this is going to be C31 minus C13 all over 4 QY tilde. This is going to be C12 plus C21 all over 4 QY tilde. This is going to be just QY tilde. This last element is going to be C23 plus C32 all over 4 QY tilde. Finally, this last one is what you would do if QZ tilde was actually the maximum value. You would have this as being C12 minus C21 all over 4 QZ tilde. And then you'd have this one as C31 plus C13 all over 4 QZ tilde. And then C23 plus C32 all over 4 QZ tilde. And finally, this is QZ tilde. Yikes. All right, we're all done. There you go. So as you can see, it's not bad. You can easily think about implementing this in a function if you like. So you basically pass in this DCM, right, which has all of the elements, C11, all the way up to C33. And then all you got to do is basically just go ahead and perform this algorithm. And that will give you the equivalent quaternion that comes out, okay? Now, if you don't want to implement all this yourself, MATLAB actually has a function called DCM2Quat. which is literally the name, I guess, right here. So that will do this operation for you. So you pass in the DCM, MATLAB will go ahead and do all this operation for you and kick out the equivalent Quaternion, okay? All right, how about backwards? What if you had a Quaternion and you wanted the DCM? All right, let's go the opposite direction. How about a Quaternion to a DCM? Okay, so the idea here is now I've got a Quaternion Q. I want the DCM, the CBV, right? I want that coming out. So I want to go from a quat to a DCM. Okay, how do we do that operation? Well, it turns out that this is not that bad. So again, Q is going to be QS, QX, QY, QZ, right? That's what's coming in. Well, to do that, you basically are going to formulate CBV. It's just going to be your 3x3 matrix. Again, let me just draw this guy out. And it's just a direct function of all those Quaternion elements. So for example, the first element is just QS squared plus QX squared minus QY squared minus QZ squared. Okay, this element is 2 times QX QY plus QZ QS. This element is 2 times QX QZ minus QY QS. Okay, and again, just to make this easy, what I'm going to do is I'm just going to continue reading out the elements so we don't have any confusion with my handwriting. So this is 2 times the quantity QX QY minus QZ times QS. Okay, this 2 element is QS squared minus QX squared plus QY squared minus QZ squared. This last one in the second row is 2 times QY QZ plus QX QS. Okay, and then row 3 is 2 times QX QZ plus QY QS. This element is 2 times the quantity QY times QZ minus QX QS. And then finally, the 3 element is QS squared minus QX squared minus QY squared plus QZ squared. So there you go. This is basically the way to take the Quaternion, turn it into a DCM. So again, MATLAB has literally the quat to DCM function here. So you can basically do that directly in MATLAB as well. All right, so let's go one level deeper in the sense that what if I had an Euler angle and I wanted to turn this into a Quaternion? Maybe we should have added the adjective Euler in front of this. Euler angle to Quaternion, okay? So again, the picture that goes along with this is I have a Euler angle, which we were calling capital phi. So this was phi, theta, and psi, right? And I want to do some computation and turn this thing into a Quaternion Q, okay? Okay, and this is like I want to go from an angle to a Quaternion, okay? If you think about this long enough, this isn't actually that hard because in our previous discussion, we already know that basically if you have the Euler angles, you already have the DCM, right? There's already a mapping which says CBV, right? We actually derived this earlier. It's again a big giant 3x3 rotation matrix, which is the product of three individual rotation matrices about X, Y, and Z axes. This thing looks something like cosine theta, you know, cosine psi, cosine theta, sine psi, you know, minus sine psi. Sorry, theta. I won't fill in the rest of this because we already discussed this in one of the previous lectures, but it's a formula, right? It's 3 rotation matrices multiplied together to get you this big ugly thing, right? So you can already do that here to get, you can do the operation to get a DCM, right? So you could take the Euler angles, turn it into a DCM a la this, right? This is basically that operation. And then, you know what? Didn't we just talk about a DCM to a Quaternion? we just talked about how to do that. In fact, that's DCM to quat, right? If you were too lazy to implement the algorithm we just talked about on the board, just have MATLAB do this thing for you, right? So it's actually not too difficult to do this, and as you can probably imagine, MATLAB has already got this implemented as well, this workflow. So there is literally an angle to quat function. That being said, we better be a little bit careful with this. Let's go ahead and jump over to MATLAB and read the documentation on angle to quat.
All right, so before using the angle to quat function, we should do like any good software developer does, and RTFM, which I'm sure you know stands for read the something manual. I'll let you Google that if you want. But anyway, we should say help angle to quat. Okay, and if you look up this reference page, this all seems pretty reasonable. It says it calculates a quaternion for a given rotation R1, R2, R3, right? And these are basically the three Euler angles, as you would expect, for a given rotation sequence. Now remember, we talked about earlier that the rotation sequence that we are interested in is a ZYX rotation. And luckily for us, the default rotation is a ZYX. So we could actually call it using this first variation of how to call the angle to quat, where all we need to do is pass in the rotation angles R1, R2, R3. Now, this is where there's a slight gotcha. You got to think about this. What is R1? R1 is the rotation associated with the first axis, or associated with Z. R2 is the rotation associated with the next rotation about the Y, and R3 is the rotation about the third one, which is X. So really, the order in which you call angle to quat is they actually outline it for you right here. You call angle to quat, you give it psi, then theta, then phi. So again, the reason I call this out is because in some cases, you know, I think we spoke about earlier, mostly in aerospace, the standard ordering of this is phi, theta, psi. But you better be careful that you put in actually psi, theta, phi when you call angle to quat.
All right, so we saw that the only thing you got to be careful with when you're doing angle to quat is the order of the input arguments, right? So usually what you're going to be doing in MATLAB is you're going to go angle to quat, right? And then you're going to go psi, theta, phi. Oh, excuse me, phi, right? The reason I bring this up is because, right, we talked about this earlier, is that the standard order in most aerospace applications is phi, theta, psi. So again, this is one of these places where you just got to be a little bit careful of what you're doing and make sure you are using the software properly, okay? Okay, with that being said, let's go ahead and do the last one. All right, so the last one is how do we get a quaternion to an Euler angle, right? So again, workflow, as you can probably imagine, is I want a quaternion coming in. At the end of the day, I want Euler angles in the order of phi, theta, psi coming out, okay? So I want to go from a quat to an angle. Okay, and again, this is not that difficult because we already had the workflow that would be able to take you from a quaternion to a DCM, right? This was quat to DCM, right? And now, once you have a DCM, we can extract the Euler angles. If you remember from our previous lecture, we said that given the DCM, the bank angle, or the bank Euler angle, was just A tan 2 of C23, C33. Theta was just negative inverse sine of C13, and then psi was just A tan 2 of C12, C11, right? So this was how, if you were given a DCM, you can extract the Euler angle. So this is basically right here, right? It's like a DCM to Euler. I don't think that's actually the function of MATLAB. I'm just kind of illustrating it. It's basically, it's this, right? You stick these three equations in this block and ba-bam, here you go, right? Yeah, I think that's good. Again, as you can probably expect, MATLAB has the quat to angle already, but like we did last time, we better go ahead and RTFM. Let's pause and go read the manual and see what it says about this.
All right, so let's do the same thing and say help quat to angle. And again, this is similar to what we saw earlier, but if you pass in a quaternion Q to quad-2 it's going to give you the three rotations, R1, R2, R3. Again, using the default understanding of the ZYX rotation, the only difference now being, again, R1, R2, R3 are rotations about the ZYX active respectively. So in other words, it's going to return to you three numbers. The first number is going to be the yaw angle, the second is going to be the pitch angle, and the third angle is going to be the roll angle. So in other words, it's going to return the Euler angles in the order of psi, theta, phi.
Okay, so again, we saw that there's an interesting thing that we need to think about in the sense that quad-2 angle, right? If you call quad-2 angle, right, and you give it Q, this thing is spitting out psi, theta, phi. Right, so it gives it again in this sort of interesting order. So all you have to worry about is that if you are wrapping this up in some model here where you've got Q coming in and you're calling quat to DCM, right, what you're going to get out of this is don't just blindly take these three elements and assume they're the Euler angles in the proper order. It's actually going to give you psi, theta, and then phi first. If what you want coming out, right, is the Euler angles in the order phi, theta, psi to be standard, right, you got to do a little bit of just rearranging, right? That's pretty dumb. It's this one just goes straight. You got to swap these two. So again, just don't mess up the order in your Simulink models or your MATLAB code by forgetting to take this into account, okay? All right, so actually, this might be a good time to revisit that exact same example we were looking at earlier, and we can dig a little bit deeper now. So if you remember, here were the Euler angles. So if you think about this, we now have got the machinery in place that we can go ahead and calculate a quaternion that is associated with these Euler angles, compute the associated axis of rotation, and also compute the associated transformational/rotational angle to get to this equivalent rotation. So if you think about this, this is sort of like a three-step process at this point. So the first thing we can do is we can use, you know, our good old-fashioned angle to quat, or use the algorithm that we talked about earlier, and we can use this here to basically get the quaternion associated with these Euler angles. So what we're going to do here is you've got the Euler angles coming in, right? Phi, theta, psi, and what we're going to do is we're going to pass these into, or call angle to quat, obviously making sure we keep in mind what's the proper order in which to pass to angle to quat, as we discussed. This is going to get us a quaternion Q, right? What we can then do is inside this Q, it's going to have both the scalar and the vector component of that rotation embedded into it. So the second thing we can probably do here is we can go ahead and extract QS, right, which is the scalar component, and use it to compute the translational rotational/rotational angle Q using the definition, right? The definition we said was, well, the scalar component is going to be cosine of that angle over 2. So if you just solve this thing for theta, right, don't you basically have theta is, what is it, 2 times inverse cosine of the scalar component of the quaternion? And again, keep in mind, this theta is not the same thing as this theta. Unfortunate naming collision, but that's our Euler pitch angle. This is the total translational slash rotational angle about the axis of rotation. And then finally 3, once we do that, the next thing we can do is we could also go ahead and say extract the vector component, right, from the quaternion, and use to compute the axis of rotation, right, E. Again, using our definition, we said that the vector component of the quaternion was what? It was E times, it was scaled by sine theta over 2. So therefore, just solving this thing for E, we basically get that the axis of rotation is whatever the vector component of that quaternion is, but then we got to scale this thing by 1 over sine of theta over 2, right? So maybe just graphically, kind of, you want to think about this, we're going to break off QS, we're going to go break off V, then we're going to go ahead and use this formula here, right? We can go ahead and say theta is 2 cosine inverse of QS, right? And then that's going to get us that the transformational slash rotational angle. And then down here, we're going to take this V and we're going to go and say E is just going to be V times 1 over sine of theta over 2. So I guess you kind of probably need to give theta over 2 as well, and that is going to give us our axis of rotation E. Then what we can do is we can go and check. If you remember, I think what we said last time is we guessed, and we said that just by using just guess and check, I think we said that we thought theta was approximately, what was it, 100 and, shoot, I got to remember, what was our number, like 126.5 degrees. Right? And then the other thing we could do is we also saw that this axis of rotation, I think we were calling that N earlier, it was the axis of rotation that we got via eigenvector eigenvalue analysis, right? I think earlier we said that was something minus 0.4854, 0.8706, and 0.0851, okay? So this and this should match. So one thing that might be good to do is we can check to make sure that these two vectors are similar, okay? So maybe we'll go ahead into MATLAB and we'll take the cross product of these two things, because you know if two vectors are pointing in the same direction, they take their cross product, they should be 0. So let's go check that. We'll go check to see if this translational rotational angle is somewhere in this neighborhood. It should be pretty close. And we'll check that the axis of rotation that we could get via the Quaternion calculation matches the axis of rotation that we obtained via the eigenvector eigenvalue analysis. So let's jump over to MATLAB and basically just code this up real quick.
All right, so here we are back at that exact same code. I've just added a couple of extra lines to implement what we had illustrated up on the board. So I've got a breakpoint sitting right here. And what we can now do is taking our Euler angles, psi, theta, phi, again, noting the order that we passed it in, we can just pass it into angle to quat. So I'm going to go ahead and hit F10 to execute that line. And we see here's the Quaternion. Again, MATLAB likes these to be a 1x4 or a row vector, which is fine. That same information is embedded into it. So what we can now do is, like we talked about, the first thing we want to do is pull out the scalar part of the Quaternion, which is just the first element, and then we're going to use our definition to compute the translational slash rotational angle associated with this rotation. So this theta exact thing that I'm calling is basically the exact rotation angle that we need to rotate about that axis of rotation to go from the red frame to the blue frame by rotating about the magenta axis of rotation. So if we go ahead and hit F10, F10, F10 one more time, look at that. So in degrees, this is pretty darn close to the 126.5 that we guessed at earlier, but this is the exact value. So it's actually, we need to rotate in a right-handed sense. We need to go about this magenta axis of rotation. We need to go by 126.449 degrees to be precise in order to go from the northeast down frame to the body frame that has the Euler angles that we illustrated up on the board. What was that? Let me just scroll up to the top so we can remember. Oh yeah, here. 70 degrees, 130 degrees, and 25 degrees. So this is the same, this is the amount of rotation that we can achieve that exact same rotation by using a single rotation about the axis of rotation. So now, the next thing we need to do is let's get that axis of rotation. We already know what it is, again, via eigenvector eigenvalue analysis. That's this magenta line right here in 3 space. Let's just make sure that the Quaternion gives us the same information. So, again, what I'm going to do here is on line 119, we will go ahead and extract the vector component of the rotation. And now what I'm going to do is you're going to use the definition, again, that we wrote up on the board to actually get the axis of rotation by scaling that that vector component by this 1 over sine theta exact over 2, okay? So this is what we got, and if you notice, this is the exact same thing as, again, I'll scroll back up here. Here's the axis of rotation that we got as basically the eigenvector associated with the unity eigenvalue in the DCM. So if we look at this, I guess n is a vertical vector, e as a horizontal row vector. So maybe to compare these on top of each other, let's just say n transpose, and then I'll put e on the bottom. And look at these. These two things are they're the same vector. They are pointed in the same direction. And if you don't believe me, we can go ahead and take the cross product of those two, take the absolute value, and sum up all of the elements in that thing. And look at that. That is basically 0. So we got the same information. The Quaternion embeds the same information. It has the axis of rotation embedded into it, and it also has the transformational slash rotational angle that we go through about that axis of rotation to get all that information. So this is awesome. It's showing the Quaternions. It's a nice, robust, interesting way to go between Euler angles and Quaternions and vice versa, but it has all that information. So now we're really cooking with fire.
Okay, so the last piece of the puzzle to complete this discussion is we need to think about how can we use Quaternions to look at attitude kinematics in a similar fashion of how we use the Euler kinematical equations and Poisson's kinematical equations to take rate gyro information and turn them into Euler angles. Is there an equivalent way we can use Quaternions to kind of get to that same result? And the great thing is yes, the relationship of how the time rate of change of the Quaternions relate to the rate gyro information, it's actually a very simple expression. It's this, it's q dot is 1/2 times omega q. And in this case, omega is going to be a 4x4 matrix. So let's go ahead and stub this guy out just so we can see what the entries look like. Okay. So on the diagonals are a whole bunch of zeros. So there's zeros all the way down the diagonals. And then in the first row we have minus omega x, then minus omega y, and then minus omega z. In the second row we've got positive omega x, positive omega z, and minus omega y. And then the third row we have positive omega y, and then minus omega z, and then positive omega x. And then finally in the last row we have omega z, omega y, and minus omega x here. So in this case we have, we're using the notation that P, Q, and R, right? Remember, these were the angular rate of omega b with respect to v expressed in the body frame, right? This was the information being read from the rate gyros, but I'm going to use the notation of omega x, omega y, and omega z. Again, to try to avoid a little bit of this naming collision, because I don't want to be using Q's in here, because Q is what we're using for Quaternion. So I don't want to use Q for pitch rate. So I'm going to use omega y for pitch rate. And similarly, I'm going to use omega x for roll rate and omega z for yaw rate alternatively. But long story short, this is basically embedding information about the rate gyros into this 4x4 matrix. So here it is. This is actually pretty great. It's very simple to kind of come up with a dynamic equation of how do the Quaternions evolve in time if given the gyro rates as inputs. So this is actually beautiful because we can now start thinking about how can I implement this guy in Simulink? How can I implement this equation in Simulink? It's basically 4 scalar first order differential equations in Simulink. So again, that's awesome. Let's think about that now. So let's think about how about an implementation in Simulink, okay? So again, I always like to start with, let's start with an integrator, 1 over s. So here's my integrator. And I'm going to try to make the signal q dot. And if I integrate that, I'm going to get q. And then apparently q dot is just given by that equation. So all I need to do is, again, we'll have a box which is, let me see if I can maybe position this in a little bit nicer fashion. Let me do it like this. So let's say from rate gyros. Okay, so what's coming in here is P, Q, and R. I guess I'm running into the naming collision with the Q. Let's call this, we're going to say omega x, omega y, omega z, right? Again, this is omega b with respect to v expressed in the body frame, right? That's the rate gyro information. That's coming in. Okay, so in order to form this, I need to first form this omega matrix. So I'm just going to go ahead and make a block here which says, how about form omega matrix? Right, so you just need something to basically take these things, jam it into this format, so out of this comes that big omega matrix. It's a 4x4 matrix, right? Okay, and then I guess all I need to do is multiply that thing with Q. So I'm just going to go grab myself a matrix multiply. Okay, like such. And again, I think we got to be careful with the order here. I think we want the first input, which is omega, the omega matrix, to be the first input to the matrix multiply block, and then we want we need the Quaternion Q, which is right over here. So I'm just going to drag this back, plug it in like such. So that's Q. So I'm almost there. I've got to make sure we don't neglect this 1/2. So let me move this Q dot over a little bit, and I'm going to need to jam in a gain block right here of value 1/2. There we go. So I think this has implemented that equation over there. Now, the only thing we need to think about is these Quaternions are great, but really we really want the Euler angles, right? That Euler angle information is embedded in this Q. So what I need to do is I need to basically extract the Euler angles here. So that's not that bad because we already know how to do that, right? We already have quat to angle, right? Here. Okay, so what's going to be coming out of this is we're going to be basically getting our Euler angles. Maybe what I should do here is let me tell you what, let me combine this. I'll say this is quat to angle and rearrange. Like we talked about, quat to angle is going to give you psi, theta, phi. Typically, we want this coming out as a vector of phi, theta, psi, just to keep the interface consistent with some of our previous discussions here, right? So you're gonna have to play a couple of tricks. Don't worry, we'll go into Simulink and do the nitty gritty there in a second. Okay, this is pretty awesome. The only last thing that we probably didn't discuss here is the initial conditions to this integrator. What is Q at time 0? What's the initial Quaternion, okay? So basically, we're going to get that. If you think about this long enough, you probably have an initial Euler angle description of the vehicle. So what we need to do is we need to take the Euler angles at time 0 and turn them into an initial Quaternion, and again, we can do that using the opposite. We can use angle to quat. Again, being careful of how we call this. So if we were able to take the Euler angles, take angle to quat, convert them into an initial Quaternion, stick that into the integrator, I think we're pretty much done with this. This looks pretty darn awesome. If I box this whole thing up, right? This should look very similar in terms of the interface to what we looked at last time. This is basically a Quaternion implementation. So, you know, we had Euler's, the Euler kinematical equations, the Poisson's kinematical equations, and now I guess we've got the Quaternion kinematical equations, which is just another, again, a third way to go about consuming rate gyro information and spitting out Euler angles of the vehicle and maintaining the Euler angles of the vehicle. So there's a couple nuances with this implementation that we might want to look at. So tell you what, let's jump over to MATLAB Simulink and build this model and compare it with the Euler kinematical equations and Poisson's kinematical equations.
All right, so here we are. I reopened that same Simulink model that we built in our last video where we implemented the Euler kinematical equations and Poisson's kinematical equations. So let's go ahead and now just create an extra subsystem, which is now going to implement the Quaternion kinematical equations. Okay, so we want the interface to be the exact same, namely I want the rate gyro information going in, so that's omega BV expressed in the body frame, and I want the Euler angles coming out, which is capital Phi. Okay, so we just need to make that mapping, which is basically what we had on the board earlier. So let's go ahead and do that. So I'm going to go ahead and start with an integrator, And this is going to integrate our quaternion, so I need an initial Q0 as our starting state. We're going to have to define that later. The next thing that we might want to do is form that Q matrix, the omega matrix, excuse me. So I'm going to go ahead and come to my Simulink library browser, grab my MATLAB function block, because that's an easy way to build a 4x4 matrix. I'll just double click on this and go ahead and build that. Now again, to maybe make it so you don't have to watch me input all of these myself, I'm just going to say that omega b VB comes in and we want omega coming out, and the way we're going to do that is I prepared this kind of off screen so you don't have to watch me type all of this in and make transposition errors and all that stuff. But this is basically what we talked about on the board. I'm just going to pull out omega x, y, z and then form that 4x4 matrix. Okay, so I'll go ahead and save this and close it and come back to the Simulink model and keep building. So what this guy does is it forms the omega matrix. Okay, so the next thing I'm going to need is a matrix multiply that we talked about on the board. I'm going to multiply that matrix with Q, which is that signal, and then if I hit this thing with a gain of 1/2, what we should be able to do is now finally get Q dot. So that's this signal here is Q dot, and coming out of this should be Q. Okay, and maybe this is a good spot to leave it for now. Let's go ahead and put a scope on this for now, just so that we can see if we're actually calculating quaternions successfully. So you notice this is red because it has no idea what the initial condition is. So let's go ahead and define that now. So I'll move over to MATLAB. Here's the script that we had defined earlier, which it defined the initial Euler angles for Euler's kinematical equations. We then turned that into an initial DCM for Poisson's kinematical equations. So let's do a similar thing and basically define initial quaternion for the quaternion kinematical equations. Okay, so that says Q0 is, we're just going to use our good old friend angle to quat, and we're going to make sure that we remember that it's actually psi 0 that goes in first, and then theta 0, and then phi 0. So if we run this script, we should hopefully have Q0 defined. Great, here's our initial quaternion. All right, so let's go ahead and come back to the Simulink model over here, and I think we should be pretty much good to go. So if we go ahead and run this, let's see if it runs. Okay, it ran, and I actually turned on signal dimensions. That was up here in view. I always forget where this thing was. I always have a hardest time finding that view. Man, where is this thing? Is it, no, it's display. Here we go. It's display. Oh, here, signal and ports. Yeah, signal dimension. So I turned that on so I can see what this is. This is a 4x4 matrix. This is a 4x1. Now that's a little bit interesting if you think about this, because over here, this quaternion, this initial Q0, you just saw it in MATLAB. It's actually a 1x4, but for whatever reason in Simulink, this gets turned into a 4x1. That's going to have ramifications later on down the road. But anyway, this ran, and if we double click on the scope, you can see that, yeah, we're propagating quaternions fine during this. Now, the only thing that we would like to do now is, quaternions are a little bit hard to understand, right? They embed information about the rotation angle as well as the axis of rotation, as we saw earlier. I really need to turn this into phi. So really, what I need to do is put in here, I need to make a call to quat to angle. Right? That is going to allow me to take that quaternion and turn it into an Euler angle. So you may be tempted to go ahead and try to grab, again, a MATLAB function block and basically hook this up. And you may be tempted to basically try to double click in this and basically say, okay, coming in is the quaternion, coming out is phi. So all I need to do is basically make a call to quat to angle, pass in Q, and then get psi, theta, phi, right, in that order, and then repackage them or rearrange them. Rearrange to get the capital phi, which was going to be phi, theta, psi. Okay? Now, a couple of nuances here. One here, the quat-to-angle, again, if you read this thing, quat-to-angle, we're a little bit careful. MATLAB wants these things to be m by 4 matrices containing m quaternions. So in this case, we have one quaternion. So I need Q to be a row vector. In this case, in Simulink, Q is being propagated as a column vector. So I need to stick a transpose on here in order for this to have a hope to work. So let me go ahead and save this. Okay. And now if we come back to the Simulink model over here, I can try to run this, but it's not going to like it. So I hit run and it chokes. And it chokes right here because as of MATLAB, I think I'm running 2018B, functions like quat-to-angle or things like that are not supported for code generation. What happens with these MATLAB function blocks is when you hit run in Simulink, it actually tries to auto-code it a little bit and compile that out. So it needs to interpret the contents of this. So you can't use every single MATLAB function within this is really confusing. You can't use every MATLAB function within a MATLAB function block. So in this case, we see that you can't use quat-to-angle within this. Now, there are ways to get around this, but I think the easier way to do this is just don't use this MATLAB function block to make this call. So instead, what I'm going to do is let's copy all of this code. Okay, copy this so we don't lose it. And then what I'm going to do is come back to the Simulink model. I'm going to delete this MATLAB function block. And instead what I'm going to do is I'm going to grab an interpreted MATLAB function block. So if I drag and drop this in, what this is going to allow us to do is it's going to allow us to make a call to some other MATLAB function which is defined outside the Simulink environment. So why don't I call this, how about wrapper quat-to-angle. Okay, so I'll make some function called wrapper quat-to-angle. And what I can do now is come over to MATLAB. Let me go and pull that up. Start a new script, and I'm going to say function crud. What do we call that? Wrapper quat-to-angle. Okay, and that's going to take in a quaternion, and it's going to spit out phi. And this is basically going to be the code. I'll just paste it in here. This is what we had in the MATLAB function block earlier. So it's doing the same functionality. We got the transpose and all that kind of good stuff in here. Don't forget this transpose. This killed me a couple of times. It took me a while to track this down. But long story short, hopefully this should work at this point. So let's go ahead and hit save. And I'm going to put this in the same folder where I'm executing it. I'm going to call it, wrapper quat-to-angle. I'll go ahead and hit save. And now, let's go back and we will clear everything and reinitialize everything. And, okay, I think that ran. Let's go back to my model. And again, now what we see here is we've got this interpreted MATLAB function, which is basically a wrapper to the quat-to-angle function call. Okay, so now if we go ahead and run this sucker, give it a second, and there it goes. It ran. Dimensions look reasonable, so let's go up a level. And now what we should do is let's do a comparison to make sure that the Euler angles computed via the Quaternion method all line up with the ones that are computed via the other two methods. So what I need to do here is, if you remember, what this scope on the side was doing was comparing. This here is the phi angle, right? This is theta, and this is psi. So now what I was doing earlier, I was comparing the Euler kinematical equations to Poisson's kinematical equations. Well, let's tack in one more comparison. So I'll add 3 to all of these, add a dimension to make them have, each of these muxes have 3 inputs. And what I will do is we will use the Quaternion method as the third input to all of these. Okay, so sorry, I apologize. This is getting a little bit spaghetti-like, but if I save this and run it, and now come to this main scope, drag it over. Look at that. Isn't that beautiful? It is pretty much working. So again, on this left column, these are the rate gyro information. Here's P, Q, and R. And now we're using 3 different ways to compute the resulting Euler angles of the system. So again, we see that phi, the bank angle, all 3 of them are identical. Same thing with theta. And then psi, we've got the wraparound issue where I believe the Euler kinematical equations just kind of keep on integrating. But with Poisson's kinematical equations and the Quaternion method, we've got the 2 pi jump, which really is of no consequence. So with that, if you come back to this, I think this is a great spot to leave it, because if you look at this now, we've got three different ways to achieve the same goal of consuming rate gyro information and then tracking and computing what the resulting Euler angles of the system are. So each one of these have their benefits. I will say that the Quaternion method is probably the most robust method. It's not subjected to those problems of, say, gimbal lock or issues where there are singularities at odd orientation. So from a simulation and implementation perspective, I think the Quaternion method is the way to go. However, we saw that it's also the most complicated. There's a lot of these transforms between Euler angles to Quaternions and back and forth and etc. So that might have some ramifications. Also, later on down the road, when we're going to want to trim these vehicles or come up with simplified models, it might be easier to actually use the Euler kinematical equations, even though we know that there are potential issues at odd orientations. Hopefully, we're not going to reach those very often. But anyway, what I'm trying to say is, in your toolbox, it's nice to have a couple of different tools so you can use the appropriate one for the appropriate scenario. And I hope we've discussed and illustrated some of the pros and cons of each one of these methods in the last several videos talking about Euler angles and the associated kinematical equations to actually implement Euler angle computation. So, with that being said, I know this was a lot to consume here. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll down a little ways and click on that subscribe button, it really does help me continue making these videos. I'm going to have a lot more videos coming out in the future, also continuing on our topic of flight mechanics. There's a playlist, in fact, of all the flight mechanics videos that you may find interesting, and I'll make sure that a link for that pops up at the end of this video. But that being said, I hope to catch you at one of these future discussions, and until then, I think I'll sign off. So, talk to you later. Bye.